I am the program lead for security and technology at Unidir, and it is my pleasure to welcome you today to our side event, to the formal sessions of the GGE on laws. As you will have noticed, you just received a pop-up message to say that the event is being recorded. It is, in fact, our intention to make the recording of this event available on our site, our website afterwards. So please feel free to share the link with colleagues that could not be attending today. As I said, it is our pleasure to welcome you to this virtual event that will focus on the issue of data. And we've seen over the course of the week and last week as well, for those of you who had the opportunity to follow the discussions within the GGE on laws, data has been directly or indirectly one of the core issues of discussion, whether in relation to the problem of potential bias, but also in relation to the way in which data is a determinant of performance of autonomous systems in different stages, whether it is the development, the testing and evaluation, or the final deployment on the battlefield. We have identified, and many experts have identified, the critical role that data is playing on in autonomous weapon systems. So today's event is really an opportunity for us to dig a little bit deeper with the help of two expert speakers on the subject, following a report that Unidir released earlier this year in spring with the title of Known Unknowns, Data Issues and Military Autonomous Weapon Systems. It's really here an opportunity to try to understand a little bit better why is data so important in discussions around autonomous weapon systems. What kind of risks does data pose? What kind of data issues could arise in the development, testing, and deployment of weapon systems? And if there are any mitigation strategies that we could pursue in trying to address some of these risks? So I will not indulge in opening remarks for too long. I think it's we have limited time, and it's important that we put it to good use with our expert speakers. But before I give them the floor, I just wanted to thank SecTech donors, Germany, the Netherlands, Norway, Switzerland, and Microsoft for supporting our work on AI and autonomy. And I would also like to invite you to use the Q&A function on the Zoom interface to ask questions throughout the presentation. We will try to block a window at the end of the briefings to allow you to interact with our speakers, but please do not wait until that opportunity and start populate the Q&A panels with all of the questions that you may have. And I'm sure our speakers will do their best to make sure that you get the answers that you need. So without further ado, I just give the floor to my colleague Arthur. And Arthur, please, you have the floor.
Thank you very much, Giacomo. Good afternoon, everybody. Welcome to this event. It's wonderful to have you here. My name is Arthur Holland-Michel. I am an associate researcher in the Security and Technology program here at Unidir. I focus on our portfolio on artificial intelligence and autonomous systems. I am also the author of the report that Giacomo just mentioned, which really is the kind of anchor for today's discussion. And I am absolutely delighted to have with me today to talk to you through all of these issues, Dr. Maria Vanina Martinez. And we are tremendously lucky to have her here. She is really at the forefront of a lot of these questions and considerations. I'm going to give you a very top level run of the show for today's discussion. Vanina and I are going to talk for about 25-30 minutes, really to give you the fundamentals of what we mean when we say data issues as they relate to autonomous weapons, and what are the policy implications of those issues, as well as some of the potential avenues for action moving forward. After that discussion, and this part I'm particularly excited about, we will have an opportunity to hear from you, to hear your questions, and of course, to engage and respond to them. We're going to keep this to a tight 60-minute session. And so with that being said, I think we should jump right into it. Hi, Vanina, how are you?
Hi, Arthur.
So,
For
Vanina, you're a researcher at the Institute of Computer Science at the University of Buenos Aires and a member of Argentina's National Scientific and Technical Research Council. You're also an eminent, of course, expert on machine learning and other forms of artificial intelligence. Just first, I want you to tell us a little bit about your technical research and on top of that, how you got interested in the issue of autonomous weapons.
Well, so like you said, I'm a researcher. I work in AI. I've been working in AI for more than 15 years already. Most of my work is, I wouldn't say like completely theoretical, but it's basic research. One of the good things is like I like to say that I work in AI, but I'm also kind of in the middle of AI and databases, which has given me the opportunity to always kind of ground the work that I do with actual knowing how the real data looks like. So like I said, most of my work seems kind of like basic research, but lately I've been working on issues that have like problems that have a real world impact, like could be like finding kind of malicious behavior or abnormal behaviors in social networks, or for instance, trying to identify hate speech or other forms of misinformation and fake news and see how that, for instance, they propagate in social networks. So that's basically what I do most of my days. But some years ago, I realized that it was all fun to work with these models in the lab, but then people were actually using them in the real world, and they were trying to solve hard problems, especially building systems that would have some degree of autonomy, and they would do things like make decisions that before were mostly done by humans, right? And then I started to think, this is nice on one side, but this is also quite dangerous, because I know that the technology, it's still, I mean, it's very disruptive, but it's very new, and there's still a lot of things that we don't know about it, and we don't know how it will evolve, and we don't actually know the impact that it can have when we put it there in the real world. So it's not something that you just can take out of the lab and build a system and make it take decisions on your behalf. At least that's not the rigorous way in which I think we should do it. So I started to try to find ways to talk to people in different areas that actually make the decisions of using AI, and talk to them and explain these kind of things in order for them to be able to make an informed decision on when and if they actually want to use AI for their developments. And this is especially critical for systems like any military device or autonomous weapons, right? So that's how I basically started doing this.
So I'm going to pick up on one of your phrases, and thank you for that overview, which is the implications of taking things from the lab into the real world. And I think that's going to be a bit of a running theme in our discussion today. You were tremendously influential in the creation of our report, The Known Unknowns. You were one of the subject matter experts who advised me on the substance. You're also a reviewer. And more broadly, your work has just been very inspiring to me for a long time now as I've looked into issues in this field. Now, one of the key things that your work and that of others has taught me is that autonomous systems are essentially data processing systems. That is, in order to get an autonomous system from the lab and make it work in the real world, that autonomous system has to take in data from its environment collected through sensors, say like cameras or radars, and make sense of that data. So if you think about it in that sense, you know, autonomous systems really do become dependent on the data that they ingest. And if the data are bad, if there are problems with the data, the system will fail. And so I was wondering if, based on that, you could just run us through some of the main data issues that autonomous systems will encounter in the real world, especially in, say, a military conflict environment.
So yes, basically, there was this old notion in computer science that the brain of the systems are actually the models, right? But now this has changed because, like you said, like data is a fundamental part, and even if you have a perfect model, you don't have the right data, it will not work for the purpose that you built the system, right? So data is an issue for basically any software. For autonomous system, it's actually quite critical because so data in autonomous systems has we can think of them like in two phases, like the data that teaches the system how to behave, and from where the system learns how the world looks like, and then the data that comes like in a feed whenever the system is actually actuating in the world, right? And we can have problems with data in both phases. One is in the kind of like the design and implementing phase of the system, in the life cycle of the system, and then we have the other part where it's when the system is already deployed and working. And in both cases, data is basically, and this is, I'm talking now as a database person, it's always incomplete, low quality, and incorrect. One of them is always, you're always going to find something like that in your data. And that's a big problem for, like I said, any software system. But when you have an autonomous system in which this data is actually guiding the behavior without any intervention of human or any human in that process, this is a complication, because the system might not realize what's going on and may not have the means to do something in regarding that, right? So for instance, when I say incomplete data, what I mean is that there is like either the data with which the system was trained or the feed that the system is getting through the different sensors doesn't have a complete picture of the world in which the system is immersed, right? So like you can think like this could be because the system doesn't have the actual sensor that needs to see that, like perceive that, or because the sensor is, for instance, blocked. I don't know, like you can think of an autonomous vehicle that its camera, it's blocked somehow, it's dirty, and so then you cannot see what's on the right. And that happens all the time, especially when your system is going to be out there in the wild, right? That either you didn't think that you might need some kind of sensor to perceive data, and then it will be incomplete by design, or it could be the case that it's incomplete because something happened and you're not getting that data completely. On the other hand, you might have the sensors might be working, but then you get low quality data. And that also can happen because, I don't know, like the lenses are dirty, for instance, right? So you can imagine like a flying autonomous vehicle that is trying to land somewhere. So it's like looking at the image that it gets from the feed, like it would be a camera or something, or combination of sensors. And then for some reason, the communication is bad, the channel is bad, and then it's getting low quality data. And the picture is kind of like very few pixels, and then it won't be able probably to realize if it's a safe place to land. Or in the worst case, it might actually decide that it is a good place to land and not realizing that there is a danger right there, right? And then the other property that is used for data issues was incorrect, right, or false. This can happen for many reasons. Again, it could be faulty sensors, or like they're not calibrated or something like that. So they're not actually given the system the actual state of the world. Or the most complex one, actually, in terms, we were going to talk about that later, but in terms of like trying to mitigate it, it's like when the system is being fed false information on purpose, right? Like you can think of any, like an adversary somebody that's trying to fool the system. And people always come up with very interesting and innovative ways of trying to fool anybody, and especially a software system, right? So these are the issues that have to do with the data itself. But then there are other things that are related to data and the models of AI that we are using, that have to do with the way they work, the models, how they work. Like machine learning models, they basically trying to find patterns that are significant in the data, and then they reproduce that whenever they are asked to do something, right? And this is very fundamental to think about how brittle the systems that we're building are, is that the system always will see just a small part of the data that it needs to actually behave correctly, or how we expect in the world. Even if the data that we give to the system is huge, it's always going to be a small part of it, because unless you are working, or your system is working in a very, very controlled environment, with basically not dynamism at all. Otherwise, no matter how big your data is, it's always going to be a small part of what the system can actually find in the real world. So it's like it is blind in some way to most of the phenomenon that it's going to find outside, right?
So I might just jump in there, Vanina, because
Yeah.
I think that is a good point to sort of reflect. I remember that when we had our initial conversations during the research for the report about these types of data issues, I was thinking about these data issues as you're explaining them to me, and I was thinking, wow, I mean, a conflict environment is probably going to be a terrible place for an autonomous system that is going to be sensitive to these types of issues, because it's a very dangerous and dirty environment. There's going to be a lot of smoke, there's going to be a lot of dust, there's going to be a lot of contamination, there's going to be a lot of incomplete data, but also, as you mentioned, there is going to be an adversary that intentionally wants to fool the autonomous system by feeding it false or incorrect or incomplete data. Not to mention the complexity of the battle space, which, as you just mentioned, is really hard to kind of capture in the reduced data set that an autonomous system is kind of built on or trained on. And so I wanted to take all of that and kind of crystallize it around, again, this running theme of taking autonomous systems from the lab and putting them in the real world, because you talked about these two sort of buckets of data that are relevant: the data that a system is built on, tested on, developed for, and then the data that it encounters in the real world. And if a system, to put it very simply, encounters something in the real world that was already captured and reflected in the development data, then chances are it will be able to deal with what it has found in the real world. It knows about it, it has quote unquote experience with it. But of course, if there's a discrepancy, there may be problems. And all of these issues sort of, in a way, it seems like come down to a discrepancy between what the system has encountered in the lab and what it is encountered in the real world. And so I was wondering if you could tell us a little bit more about this sort of fundamental idea of discrepancy, and particularly how it relates to a word that we have heard a lot in these discussions, especially within the context of the GGE, which is bias. You know, how do these two relate, and sort of what does this mean moving forward for autonomous systems and their ability to operate in complex environments?
So bias, this is very interesting because from a technical point of view, bias has a very a definition that's absolutely related to what you're talking about, like the discrepancy of the data that we have and the data that we expect, right? But lately we have been talking of a different kind of bias that it might be confusing. And we're talking about like things like societal bias, right? So, and this has to do with the effects that an algorithm can have on some part of the population, right? And there are many reasons for that. One of the reasons may be because the data itself reflects somehow some form of prejudice, of societal prejudice, right? But the meaning of bias that we are talking now today, it's quite more general, in the sense that we are talking that what we are saying is that basically we train our algorithms to behave based on a portion of the data that represents the real world. And then it might be the case that knowing only that portion of the world, the results, the solutions that the algorithm gets are biased on that representation of that little part of the world, and do not actually represent or achieve the actual result that we wanted. I hope I didn't complicate the definition there. But basically what we're saying is that there is, like you say, that this discrepancy on the data that we feed the system to train the system and how it learns, based on what it learns, how to behave, and then the actual data that the system gets. And we say that it's biased because it will always respond based on what the system knows. It cannot, so that the technology that we have today cannot go outside of the realm of things that we taught it, right? It's not like it will find something different and start trying to make assumptions or conclusions about what it could be. I mean, if it's something that it never saw, it will not realize what it is. It might be something that it's similar to something that the algorithm already saw, so it might say, oh, actually I think it's this, and make a wrong decision, but it cannot invent in a set like new things that never saw. So
Sure.
This is the kind of bias that we're talking about.
Yeah.
An example of that, I mean, you can see the repercussions of this problem in society and decision making in societal problems. But it's in a sense it's more general than that, right? So the problem is that we are teaching our models with just showing it a little part of the world, so we cannot expect it to behave differently. It would always try to solve the problems in the same way it was taught to do it.
Yeah. And I think it's a really important point to pause on, because the technical forms of bias that you described can, as you say, translate into societal bias. And this may not even be technical algorithmic bias, as they say, or statistical bias. Bias is not necessarily something that just exists in machine learning systems. For example, an example that came out a few years ago was an automated soap dispenser like you have in bathrooms that used an infrared sensor to detect when a person's hand was underneath it. And it performed much worse on people with darker skin. Now, has nothing to do with machine learning, but there is a sort of bias in the sense that the system was developed for a small segment of the entire world or entire population that it might actually encounter, in the same way that an autonomous system that is only designed to operate in, I don't know, snowy environments is not going to perform well, say, in a jungle. And this, if you'll indulge me, it goes to sort of one of these the fundamental findings of the report, which again you were so helpful in helping us reach, which is this notion of the known unknowns. You know, to try and sort of condense it, as you have been explaining it to us, autonomous systems will always be based on just a small subset of data representing the entire totality of possible data that it can encounter in the real world. It will have some form of bias, whether that be societal or not. And as a result, it will fail in ways that we cannot predict. Obviously, if we knew that a certain issue was going to be present, we'd design it to deal with that issue. And so in a way, we know that these systems are going to fail, but we do not know, here is the unknown part, how they will fail, when they will fail. And of course, because they are complex autonomous systems, and because, as you said, they don't have any awareness or understanding that they are encountering an issue, we also don't know exactly what they will do when they fail. In the context of conflict, this could potentially raise real issues around responsibility, right? If a military deploys an autonomous system, you know, and they have to have, in the verbiage of the GGE, you know, full contextual awareness. They have to have full risk mitigation, testing that reflects the environment that the system is going to be deployed to. Even then, the system may encounter issues that they couldn't have possibly anticipated. And yet they know, because of these realities that you're talking about, that it will fail in one way or another. And so when it does fail, there are all kinds of issues about whether they are or are not responsible for those failures, whether it would or would not be legal under international humanitarian law to deploy something that you know will fail. You just don't know when or how it will fail, and the testing techniques are not necessarily up for it. I just wanted to put that out there because that is really where your world and our world intersects. And you were talking earlier about how you saw the implications of what you were doing in the lab once translated into the real world. And for the purposes of the GGE, we feel like this is an important consideration, how data issues create implications for notions of the application of international humanitarian law and the ideals of responsibility and accountability. But of course, we don't want to end on that note. We want to talk about some of our options moving forward. And that's where we go back in some respects to the technology itself. And so I was wondering, in these last few minutes that we have, if you could talk about some of the options that may be available to us moving forward to address these issues that we have been discussing today.
So the research community is working very hard to trying to solve many of these problems. So one thing that that's interesting to mention is that, and this is related to what you say at the beginning, that it's actually, I think you say in your report, it's the data that is the smart part of the system. And in computer science, we have a whole area that actually works on models, trying to mathematically show that the model is correct, that given a specific input, it will deliver a specific input. And you can make sure and absolutely prove it with a theorem, basically, that it's going to be like that. When you make, but this only works, like the techniques that we have today only work for very I don't want to say small, but kind of controlled models. Like they're not quite big. But it's actually what people use for critical software, like you know, in a nuclear plant, for instance, right? They do have automation and they do have software, and they use this kind of techniques. The problem when you add data is that data is somehow like we were saying in a scenario like conflict, the different types of data that you can have, it's kind of infinite. So you cannot really, at least with the techniques that we have now, actually make sure that the system, given any kind of data, will respond in a way that we want. It's impossible. We don't have the techniques to prove that. The closest that we have, and it's the way in which we test our systems, is like systematic testing, right? And this also has to be, I mean, there are a lot of people that are working on trying to find more rigorous ways of testing AI systems, basically trying to cover as much data as possible and build distributions of data that cover most of the known part of the world that the system will encounter. And many of these techniques are actually done using simulation, because sometimes you can't find the data that you need. I mean, it's quite hard to replicate the feeds of the kind of scenarios that you can have in a conflict unless you are in a conflict, right? So simulation techniques can help in trying to show the system data points that are maybe that happens once in a while, or are kind of out of the normal distribution of things that appear in a more like common scenario, that it's not a conflict scenario. So there's also a lot of work going on in the last 3-4 years that have to do to try to measure the bias. I mean, to try to see if my data or my algorithm is actually biased. If there is a discrepancy between the data I'm feeding the system and the data that it actually will eventually encounter. The reality is that these kind of metrics, they are promising, but they are still quite in an embryonic stage. And the thing is that there is, like we were saying, there is not just one definition of bias, and in order to try to see where my data may fail or may have issues, I have to have an idea of where the problem could be. So I have to have the suspicion that here maybe related to this feature of the data there might be something wrong. So then I go and measure and try to see if that's the case or not, and then I will have to apply some other technique to actually fix it in a way that doesn't mess up the whole modeling of the system. So there is a lot of work going on in there. And then you have like even more like simpler ways in which you can try and build more robust systems, like having like redundant sensors or ways of getting redundant data just to check that this like incomplete or false data, like to make sure that you have a justified like trust on the data that you're getting. And on the other spectrum of complexity, then there are people working on explainable AI, so like allowing the systems themselves to explain to some extent what they are seeing in the world, how they interpret what they're seeing in the world, and why they are acting in the way that they are doing it. So there's a lot of technical work going on this area, trying to palliate, like to mitigate these issues. I don't want to be a pessimist about it, but like I was saying, one thing is to try and prove that a model is perfect, And another thing is like to try that model is perfect when you have infinite options of data coming in. So none of these techniques are going to actually work in the short term. They can help us understand better the technology, and they can, like, if we want to do a rigorous work, like translating the work from the lab to the real world, we have to use them, like to actually try and build the best we can. But the reality is that we don't know how these technologies are going to evolve. We assume that AI is going to be perfect in 10, 15 years. We actually don't know that. We hope it would, but we don't know that. So all these research and advancements in technologies, especially in trying to detect and fix data issues, is absolutely important, but without a structure in which we can actually make sure that it's being used in the correct way, it won't give us any real results, right? And when I say that, what I mean is like, so how are we going to make sure that we're using the right techniques to find and fix data issues? So there has to be some, from my point of view, right? There has to be some form. First, there has to be standards that we can use, that we can share, that we can replicate, and standards both in relation to data sets and benchmarks that could be quite hard for military purposes, I know, but also on how to measure all these issues and how to find these issues, right? And also there has to be some form of regulation in the way we build the systems. I mean, the same way, I always do the same analogy, but laboratories that create medicine or vaccines, for instance, they go through an internal process and a lot of testing of the product, but then to go out in the world and actually be applied to people and used by people, they go through a series of very rigorous protocols that they have to pass. The impact that these models or these systems can have are, if we think it could actually be in the same level of risk or even more than a drug. So why don't we do that somehow? I mean, it's difficult. It's not something that we have had time to think about it, but maybe this is the time to do it. Without that structure, I see it very hard for all the actors that work in the development of this kind of systems to be able to actually be sure that they are building trustworthy technology.
Thank you so much, Benina. I think that was a really valuable overview, not just of the individual pipelines of action on a technical and non-technical side, but also the importance of a sort of holistic approach. I'd also direct our audience again to the report and our key recommendations at the end, which were built in large part on some of Benina's valuable input. But at this point, I think it would be a really good time to actually turn to our questions because they are coming in like nothing else. And there are some really excellent questions in here. I'm going to try and consolidate a few of the questions that are coming in to save us a little bit of time and to try and ensure that we can get to as many as possible. And one of the themes that I've seen popping up, Benina, in the questions has to do with synthetic data. As our esteemed audience has no doubt heard and read, there have been a lot of developments in building these gigantic synthetic data sets that replicate the real world. And so instead of having to test an autonomous system in a real world lab or a testing site, you can just give it like huge amounts of kind of like video game data in a sense, and have it explore and learn about the world in that way. What's your take on synthetic data? To what extent is it going to be a way out of some of these complexities and issues?
So I have mixed feelings about it. On one side, like I said, it's a good way to actually be able to show that the system data that might not be accessible, right? On the other hand, this simulated data, it has to follow some kind of distribution, right? And it has to be something that it's different from what the system already saw, but it has to be something that it's similar to what's going to happen in the real world. So the designer of the engineer that is working on this, building the simulated data, because that's built like any other system, will have to have an idea of how to build this distribution, right? So we're again this kind of like the same paradox, right? Like you will have to know a little bit or suspect that you are missing some features of the data in order to build fake data or simulated data to show the system, because otherwise it's just like showing random stuff to the system. It might be a good idea, but maybe also far away from what the system's gonna find outside, right?
So it's kind of that same issue of, you know, that gap between the lab, the synthetic data being created in a lab, and what exists in the real world. One of our esteemed audience members has posted a quote that synthetic data is like grading your own homework. You sort of set the challenges that the autonomous system is going to learn from, and it is a human creation in a way, that world. I do want to move on. Sorry, go ahead.
Sorry, it works for a lot of things. I mean, you can do that in order. I mean, there are scenarios where you don't have that much data, and you can use that kind of things to improve your system. I don't think it is the way out of the actual issues. I mean, not just that alone. You might need some other techniques to make sure that your design is actually robust enough.
So I also want to pick up on another question that came in that has to do with the notion that humans in battle already are ingesting and trying to understand data, and that same data can also have a lot of these issues. If a human is operating a drone, say, and there is some smoke in the image, they may they may get an incomplete data feed, right? But in your sense, and I have some thoughts on this too, but I'd be interested for your take. Why is that not a perfect parallel? Why do we think of autonomous systems differently in terms of how they handle bad data from humans in similar situations?
One thing is that, and this is related to the notion of bias, right? We are also biased as humans. And when I say bias, it's not in the wrong sense. I mean, we learn, we spend our lives learning how to behave in the world. And we have this kind of tendency to act in some another way when we run into a problem, for instance, right? And when we actually, if we are encountering this incomplete data or false data or whatever, it's the same kind of data that the system may have, we as humans have other tools to deal with it, like common sense or our own feelings. And we didn't teach that to the system. So the system we cannot expect the system to react in the same way that a human would. And on the other hand, if I, as a human, get an incomplete picture of what's going on and I make a mistake, then there is a due process to see what happened there, if I have any responsibility about it or not, which is quite different of what we can do with an autonomous system.
You know, one of the examples that I like is if you ask a child to track an object that's moving, and then that object moves behind some kind of, occlusion, the child will know that the object's going to come out on the other side, right? But
exactly.
One of the fundamental challenges in computer vision and object tracking is to have systems that can pick up the track in spite of any occlusions that you throw at it. And as you say, because children can do that, that's not something that's necessarily taught, so to speak. It goes to human powers of induction, reasoning, and so on. I do want to jump onto some of the other questions that came in. I'm going to try again and tie a few different threads together. One of the themes has had to do with the notion of using multiple types of data. One of our esteemed guests noted that targeting decisions currently are never made on one single data source. And many of the technical experts that I spoke to also came up with proposed this idea of sensor fusion as a way of making autonomous systems more robust, particularly for the identification, as a number of, again, our guests have raised in the Q&A, targets that conform to ambiguous categories, right? It may be easy to differentiate a giant building from a small vehicle, but differentiating, say, types of behavior, suspicious behavior and non-suspicious behavior. What role does sensor fusion play in that? And again, what is your assessment of how it's progressing and the kind of solutions it might offer?
So, I mean, it is a good start to have multiple sources to actually be able to build trust on what you're getting, what the system is perceiving from the world. One problem that we have with that, from a technical point of view, is that if we think of data-based AI, what could be machine learning techniques, they're not really smart at mixed fusion data. So the models that we have cannot handle inconsistency that good. They don't really understand what's going on there. They can if the designer or the engineer is knows exactly how to tweak it and set different parameters exactly, just to be able to handle inconsistency, right? Because whenever you have multiple sources of data, you are prone to have inconsistencies, right? They will be, even if it's slightly different, numbers or images are going to be different, and so you have to decide when actually those differences are important and when not. Machine learning systems that we have today may be able to do that with a lot of work from an engineer point of view. A solution that we can have is have a hybrid model that would mix machine learning with other techniques in AI that could be symbolic reasoning, kind of based on logical rules, you can say it. And this is very promising, but actually I work in that area. The solutions that we have from a knowledge-based AI models, they're still quite basic on how to deal with inconsistent data. My PhD thesis is about it. And I love the solutions that we're building in the last 10 years, but still it's something that it's quite naive, I would say. And on the other hand, from a computational point of view, it's very hard to implement. I mean, it will take a lot of time even for a small system. So
let's.
yes, we need more work.
And we're very lucky that there are people like yourself working so hard on these very tricky questions and problems. I wanted to move on to the sort of the other side, which is responding to failures or indeed some of, if you will, the non-technical elements here that can influence the pipeline. And one of the common threads throughout these questions is whether you could create standards for testing, for example, as there may be with, say, autonomous vehicles, where any autonomous vehicle, if it is going to be deployed on the road, it has to have gone through X number of training runs, it has to have been passed through X number of types of objects, there has to be a classification criteria for what kind of failures it, is known to have and how to mitigate those, but also by sort of induction from that, failures that, or by omission, failures that simply cannot be anticipated in order to create some guidelines, if you will, for the responsible development and deployment of these systems. How feasible do you see that, for example, creating standards to give a wide scope of development so that that gap between the lab and the real world can be, if not fully narrowed to a zero, narrowed in some kind of standardized way?
I think that's the only actual tool that we have from a technical point of view to actually be able to build those testing environments in a standard way that we can share. Because again, like I was saying, like testing means that you're looking for something. I mean, it's not that testing will not give you the assurance that your system is perfect, because you test for what you know, again, right? I mean, you have to have thought about the test. So the battery of tests that you're going to show the system, they are designed by someone, by a person, right? That tries to think as harder as possible in all the possible things that the system, in which the system may go wrong. Right? But then we have again the paradox, right? I mean, we know that there are things that we're not going to be able to think about. So testing doesn't assure you that the system is perfect. It only ensures you that if you were rigorous enough, you will cover a lot of situations, like most common situations that the system can find. Having said that, it's absolutely important that we develop this test beds, the test data, and the standards to actually share it between different domains or different actors or stakeholders that are building the system and using the systems, right?
I'm glad you bring all of that up, because that need to have the widest possible scope really goes to one of our key recommendations, which is knowledge sharing. If we're talking about humans having to translate the complexity of the universe into parameters for testing, the more humans you have involved in that enterprise, the larger your envelope is going to be. It is a case where working together will actually play to our profound advantage. And again, there are other recommendations in the report, again, very much guided by Nina's work and input. There was a quick question in the comments, which is a little tangential, but I just wanted to address it very quickly, which is about legal reviews as they relate to data itself. This notion that a legal review may only apply to an autonomous weapon. but not to a data processing system that actually doesn't have a lethality element. I'm going to hold back on going into a full sort of explanation on where we stand on that issue, and just point you to a wonderful report that UNIDIR put out last year called Modernizing Arms Control, which is specifically about these sort of physical embodied autonomous systems that have AI and that will influence targeting decisions, decision support systems, for example. And there's a ton of information in that report about exactly those questions that are being raised. I'm just, these questions, they do keep jumping up and down because of all the Reddit style upvoting. I feel like we've covered quite a lot. Vanina, is there anything in here that you want to, in the last 2 minutes that we have, sort of jump on?
I'm just looking. There are a lot of interesting things here. So one thing that I wanted to, like, reading through what I wanted to say is that I'm not saying that testing or simulation or simulated data doesn't work, okay? It's just that in the scenario of a conflict, the kind of situations that you can have are really infinite, especially because, I mean, you can say, well, but it's the same complexity that an autonomous car would have. Yes and no, because the whole conflict scenario, it's much more complicated, and you have another party there as well. So I'm not saying that all these techniques do not work. It's just like they actually work very well in restricted scenarios, most of them. And we have to try and find out probably new techniques for having an idea of like having the hope of these systems to behave more or less accordingly to what we want.
And I think that is an important and moderately optimistic note to sort of wrap up with. At the end of the day, what we're talking about here, again, is autonomy. And if we really think about the definition of autonomy, we're talking about systems that can deal with complexity. And that raises technical questions. And this is why I am so delighted to have had the opportunity to speak with you, Vanina, who brings such a profound technical expertise to the question. When we use an autonomous system, we are in one way or another sending it into the unknown. And it seems from everything that you have said, everything that we found in our report, that the way to narrow that gap between the lab and the real world, between the unknowns and the knowns, is to work together, to not just think about isolated solutions, be they policy solutions or technical solutions, to really think holistically about systems, not just about algorithms, but about systems of systems themselves, how they interact both with the environment, with themselves, and of course, with the humans operating them. Obviously, we have just scratched the surface today in our discussion. There are other questions coming in that we won't have time to get to, but I do want to encourage anybody who wants to continue the discussion to please reach out to me, to please, if I may, reach out to Vanina, and of course, reach out to Giacomo, who works very closely on these issues as well, and has been working tirelessly on questions around the human element in the use of autonomous systems. Our contact info is eminently available, and this is how we will continue the discussion. We'll be delighted to answer any questions that you have or respond to any comments that you might want to share. With that, my last order of business is just to thank you, Vanina, for the early start today, for joining us and for walking us through these very complex issues with such clarity. Thank you so much for your time, and thank you, obviously, of course, to everybody who joined us today. We have regular events here at Unidir. They're all broadcast virtually, so please do check in with us from time to time, sign up for our newsletter so that you can attend future installments in these series. With that being said, I'll sign off, and once again, thank you very much and enjoy the rest of your day.